Teh Hui Wen, and this is the introduction for our assignment. Modern technologies has made our lives more efficient, but it can also impact our health and well-being with the hazardous side effects. This is due to the electromagnetic radiation emitted by these devices. So today, we are going to talk about microwave detector, which is used to detect the rate of microwave leakage radiation of an oven. We are going to compare and analyze the microwave leakage radiation of an oven with and without the application of the radiation absorber. The first main component of microwave oven is microcontroller. It is a device that allows a user and a machine to communicate. It is a control unit with processing cores, memory, programmable input and output peripherals. It interprets the instructions given to the microwave oven and shows them on a 7-segment display. The next one is cooling fan. The magnetron operating temperature is reduced by cooling fans, which ensure its efficiency and lifespan. Third, we have high voltage transformer. Microwave oven requires more power. Thus, a step-up transformer with a high voltage output is installed inside the oven to accomplish this. The 240 volt supply is increased to several thousand volts and then delivered to the cavity magnetron. And then we have waveguide. A waveguide is a hollow metallic tube that leads to wave produced at the magnetron output towards the cavity. Lastly, we have the cavity magnetron. It is the most significant component of a microwave, which is a high-powered vacuum tube that converts electrical energy into long-range microwave radiations.
Hi, now I would like to explain the simulation part. First, I use the CTS Studio to run our simulation part. In this simulation, first we need to set our unit first. In this unit, we need to set our dimension in cm, our frequency in gigahertz, and our time in second. That's all for the unit. Then we need to set our frequency. In this our simulation, we set our minimum frequency is 2, and also our maximum frequency is 6. Then we can go to set our modeling. Then we choose our modeling and we press and paste our modeling at here, and we need to set our modeling Xmax, Ymax and Zmax. Then we set our Xmax is 20, our Xmax, Ymax is 20 also, and our Zmax is 2. We all in value is VCM, and we also can choose our material. And then we can load our material from library. Then example, then we set our material as wood. Then press load. Then press OK. Then now this material is wood. After that, we need to set our background. Then we only set our background this Z distance only. Then we set our low Z distance 50. Then upper Z distance is 50 also. All value in cm. Then press OK. Then after that, we go to set our boundary. Then we only set our X, Y, Z plane only. Then we change to electric. Then our X, Z plane change to magnetic. And then we need to set our wake-up rose, which represent as our transistor and resistor. So we only set Z. Then first we set as negative first, then press apply. Then the second one we put at positive, then apply. Then OK. Then after that, we can go to need to go to global property to set our maximum cell. Then we have our maximum cell set to 2.5. Then our second one cell for max model. Then we only set to 10. The third one, the minimum cell, we set to also 10. Then we press apply. Okay. Then now we can start to simulation this simulation part. we can obtain the simulation result from the S parameter. So in this simulation, we need to determine which type of material has the best absorbing the microwave radiation. So I use 5 types of material to do the simulation. First, we got use air, the PEC, which means is the perfect electric conductor. Third is the wood, and other two is the ECCO SORB N72, and the last one is the ECCO SORB JCS11. So we mark the marker at 2.5 GHz to obtain the value of the reflecting signal and also the transmission signal. So this graph is about the reflecting signal, so we can obtain the value, and also this graph is show about the transmission signal, which is as 2.5 GHz. After that, we obtain the two value of reflecting signal and the transmitting signal. We can using the observation formula to calculate out which type of material has a bad absorbing the microwave radiation. So this table is shown up using the formula to calculate out which type of material has a bad absorption. So we can obtain that the ECCORB JSC11 has the best absorbing for using absorb the microwave radiation. So after that, we can proceed using this type of material to proceed the next simulation. So we can changing for the low jet distance to try out if the distance will affect the material to absorb the radiation. So we can like change to 10 or 20 to determine the difference. So we already do the simulation, that we obtain that the from 10 cm to 50 cm they have a little bit changing of the reactive and the transmission signal. This graph is showing about the reflecting signal of value also at 2.5 GHz, and this is the transmission value of the SORB JSC11 material, so that we can calculate out that the value of distance will only have a little bit absorption different only. That's all for my part. Thank you.
Okay, so this part I want to explain the analysis of microwave radiation absorber. Okay, next is the procedure of detecting the microwave radiation leakage. In this part, the microwave detector is used to detect for the rate of the leakage of microwave radiation of the oven. Second, to conduct of microwave leakage test correctly, some items are required, which are a standard microwave leakage detector and microwave leakage level. The step below show the detecting of the radiation leakage of the oven. Let's go to step by step. For the step 1, to clear the info on the microwave leakage sensor, the 0 button is held until here and beep sound is heard. Step 2, a spacer is attached to ensure the measuring from the correct distance. Step 3, the max button is pressed. This will enable the tester to provide user with the highest readout on the digital display. This will need to be recorded on the level later. Step 4, a cup of water is placed inside the microwave oven and then the start button is pressed. Continue for the step 5. The microwave leakage tester is used to test for any leakage by running it across the edges, seals, and glass window. Step 6. The measurement value of the radiation leakage will be displayed on the digital display. This value needs to be lower than 5 microwatts per cm squared to pass the Australian standard. If this value does go above the screw holes, the leakage detector will noticeably shine in red LED light. Step 7. Lastly, the microwave test label is filled out and stick on the side of the appliance. The radiation levels, power level of the microwave, and the next test date needed to be specified. The frequency of this test is conducted yearly. Last but not least, we have the two conditions. First, condition that without using the radiation absorber. From the measuring of the power loss due to radiation leakage in several distance, the range of the power loss due to radiation leakage is from 500 microwatts until 900 microwatts, which the distance coverage is from 0.1 meter to 0.5 meter. Later, the electric field of the radiated wave can be calculated by using the formula below. The electric flux density of the radiated wave is also calculated by using the calculated value of the electric field. The formula of the electric flux density is given as below. Okay, this is the second condition with using of the radiation absorber. For the condition which the radiation absorber is implemented, which the material of the absorber is the Ecosop AN72, the S parameters of reflections and transmissions are calculated using the formula below.
Hi, my name is Muhammad Faiz bin Hisham and I will continue presenting about our findings in this assignment with discussion part. So in this part, I will presenting some of the numbers and findings that we obtained, followed by some graphs that will support our statement. This is the first data that we obtained after completing this assignment. This is the data of the microwave leakage of the oven with and without the radiation absorber. For this slide, it is the data without using radiation absorber on the microwave. As you can see, we set the distance between the user and the radiation leakage in meter by the value of 0.1, 0.2, 0.3, 0.4 and 0.5 in meter. After that, we detected some leakage power by 900 mW at 0.1, 800 mW at 0.2, 700 mW at 0.3, 600 mW at 0.4 and 500 mW at 0.5 meter. Next, we detected some electric field at 0.1 meter, which is 14.30 times 10 power of 6 and 13.44 times 10 power of 6 at 0.2 meter, 12.57 times 10 power of 6 at 0.3 meter, 11.67 times 10 power of 6 at 0.4 meter, 10.62 times 10 power of 6 at 0.5 meter. The electric flux density that we get at 0.1 is 1.266 times 10 power of negative 4, 1.190 times 10 power of negative 4 at 0.2, 1.113 times 10 power of negative 4 at 0.3 meter, 1.031 times 10 power of negative 4 at 0.4 meter, 9.403 times 10 power of negative 4 at 0.5 meter. So the quantity of charge at all this distance is 174 coulomb. So next we proceed with the data of microwave leakage of the oven by using radiation absorber. As you can see in this experiment, we set the same value for the distance between the user and the radiation leakage, but some of the value of the leakage power, for example, it is different from the without using radiation absorber. but we got the value for 0.1 meter slightly higher than the without using radiation absorber, maybe because some of the malfunction, but we got the value decreasing as by the distance. I will explain later at the graph. Based on the findings, it can be concluded that the use of radiation absorber has reduced the power loss of the radiation leakage. Furthermore, based on the result obtained, we can calculate the percentage of error of maximum power loss for two conditions of power leakage. By using formula, power leakage of initial minus power leakage of when using absorber over power leakage of initial times 100%, which is 900 minus 2363 over 900 times 100% equals to 163%. The graph illustrated on how applying a radiation absorber affected the link between the distance and power loss, as well as the relationship between power loss and electric field with electric flux density. This is the graph that we constructed by using the value obtained before. This is the graph of power loss against distance traveled by the signal. Based on the graph that we obtained, we can discuss that the link between the distance and power leakage is inversely proportional to each other. As a result, the wavelength of the radiating wave will lengthen, and in contrast, the frequency of the waveform will drop as the distance between the sources increase. In addition, it can be seen from the graph of power leakage versus electric field that there is direct proportionality between the two. In addition, the electric field and electric charge density are exactly related. Therefore, the signal electric field will become stronger as the electric field increases. Study will reveal the electric flux density of the radiating wave, which will then be used to calculate the rate of power loss via radiation leakage. In order to minimize the electric flux density of the radiating wave and lower the overall power loss of the microwave oven, the radiation absorber was crucial in slowing the propagation of the radiating wave. So that's all from me. Thank you.
In conclusion, there is a possibility for microwave ovens to leak electromagnetic radiation if they are not utilized while defective or changed. It is difficult to be detected since it cannot be smelled or seen. Microwave oven radiation injuries are only caused by exposure to large amounts of microwave radiation leaking through openings such as gaps in the microwave oven seals, so a proper maintenance will avert these problems. Based on the results obtained through the study, it can be concluded that the presence of radiation absorber reduces the power loss of the radiation leakage. Thus, we know that the radiation absorber played a role in minimizing the power loss of the microwave oven by decreasing the propagation of the radiating wave. Thank you.